Hello everyone, welcome to the channel. I am Karthik and this is the third video in a series of 50 vellum projects that I am creating. Today we will be creating a vellum abstract flower petal thingy, and let's get started. We'll start with a geometry network. Let's call it sim. You can call it whatever you want. I'll color it. You can also give it a color, and let's start with a grid. This is going to be too big for our simulation, so I'll reduce the size to 2 and 1, 2 by 1. This is our grid, and I'll also reduce the number of columns to 4. Now what we will be doing is we will be doing some modeling, but this is not going to be procedural modeling. Just select points, these points, press T and increase the size to 1.6. When you press T, you are getting this edit node which helps us to manipulate the geometry. We will repeat this process. Select the points, press T, and then you can manipulate the geometry again. Select the points again, press T, and this time reduce the size to 0.6. So this is our base geometry of the petal. Now I'll just create a transform node, and you can see that the base of this petal is not at the center of the world, so I'll just move it in the negative x direction, and now the base of the petal is at the center of the world. I was using W as the shortcut for X-ray mode. You can do that if you want. Now I'll create an attribute triangle because we will be creating a mask along the x-axis of this petal. I'll write this code: vector mask is equal to rel point b box. 0 is our geometry and p is our attribute, position attribute. So this is our mask, and we are using the rel point b box function to create a mask, but this is going to create mask in all the axes, all directions, but we want the mask in specifically x-axis. So create mask x is equal to mask dot x, and now we can create a attribute called mask which will be equal to mask x. You can see the attribute mask by activating it from here. So this is our mask attribute. The only thing is that if you choose the marker here, you'll find that the mask is running from 1 to 0. That is, at the base of the geometry, the value of the mask is 1, and at the end of the geometry, it is 0. We want the exact opposite of that. So what I'm going to do is I'll come to the attribute triangle, and in the attribute mask, I'll subtract this mask x from 1, and this will invert the values of mask that we had earlier, and now at the base of the geometry we have 0 value, and at the end of the geometry we have value 1. This is what we wanted. You can also change the color. So at the base the color is black, that is 0, and at the end the color is white, which is the same. It means the value is 1 here. Now what we are going to do is we'll use this attribute mask to color our geometry. Come to color type and change it to ramp from attribute. Attribute is mask, and this is the color that we are getting. We can change the black to this color, and we will need white at the end, but in the middle we can make it a bit yellow. Let's make it a bit darker. You can choose your own colors. So I'll just reduce the saturation a bit, and this is looking fine. So these are our colors. I'll subdivide this geometry with the help of a subdivide node. Make the depth to 2. And now I'm going to choose a bunch of edges here. So I'll choose every third edge in this geometry. And you can just click on any of the edge and double click it while pressing shift. Keep in mind to press shift while you are selecting all these edges. Now that we have selected all our edges, we'll press tab and use a transform node, and I'll just transform all these edges in the positive y direction, just like this. Then I'll press tab again and I'll use a poly bevel node. So all the edges in our poly bevel node are selected here, and we can increase the distance to 0.012 and also increase the divisions to 2. So this is our geometry. This is what we are getting. Let's increase and let's create more instances of this geometry, this petal thing. And we can do that with the help of copy and transform node. So let's create 5 instances for starters, and we have 5 instances of this petal, but they are sitting on top of each other because we are not changing any of the transformations here. So let's rotate it a bit in the z-axis. I'll rotate it 8 degrees, and this is what we are getting. Let's increase the total number of instances to 45, and now this is what we will get. These are our petals. I'll do one more thing. I'll use a fuse node so that all the points that are sitting in the center will just fuse with each other, and that will make it a whole big geometry. 0.0. I'll increase the snap distance to 0.01. So you can see that we had earlier 35,685 points, and now we had 32,089. So almost 3,000 points are fused together. So this is our geometry. Okay, so now that we have fused the center points all together, this is a whole big geometry, and we can animate it however we want. So use a transform node, and we will animate this whole geometry rotating in the z direction. You can do it manually by setting a keyframes, but that is not I'll be doing. I'll use a sine function for the frames in the z-axis. Let's see what will happen now. You can see that the geometry is rotating a bit, but it's not enough, so multiply it by 60. So this is rotating. So this is rotating in the positive and then again rotating back to the negative direction. That is okay. I'll just multiply it by 55 and let's see what happens now. So yeah, now this is working fine. I have set my frames to 150. Yeah, if yours is 240, you can just click here and press 150. And this is our animation. This is all good now. Let's use a group node and we will put them all together in a point group. Group type needs to be point, and let's call the group Petals. Now that we have our geometry, we will use Vellum constraints and Vellum solver for our simulation. So after the group, we will create our constraints. So Vellum cloth configure node, Vellum cloth constraint, and we want now pin to target constraints, but we do not have Vellum pin to target constraints here. So what we are going to do is we'll just use Vellum constraints node, Vellum constraints, this, and the Vellum constraints node will come to the constraint type and change it to pin to target. Do this, and after this we'll use Vellum solver node, and in the Vellum solver node come to forces and just remove the gravity altogether. We don't need it. Use a pop force inside, dive inside the Vellum solver, double click, and use a pop force node and increase the amplitude to 0.88. Now let's see what this Vellum constraint node is doing. We have changed the Vellum constraint type to pin to target, and now when we come to pin to animation section, you'll see that the pin type is set to permanent, which is the default setting. Choose the soft constraints here. Change the pin type to soft, and you can see the stretch section and the bend section are getting activated here. So what is happening here? Also turn on the match animation and let's run the simulation. So we can see that the geometry is following the animation that we earlier set with the help of a transform node and sine function, and the pop force that we have given inside of a Vellum solver is not affecting the geometry at all. So that means that the geometry is not taking part in the simulation at all. When we come to Vellum constraints, when we change the pin type to soft and turn on the match animation, the stretch section and the bend section got activated. So what is this? This stretch stiffness and the bend stiffness in the pin to target node works as a balancer between the animation that we have already given to the geometry and the simulation that we are trying to do here. That means the pop force and anything else that should affect this geometry. So how is it working as a balancer? When the stretch stiffness is at the maximum positive, that is 1e plus 10, that means that the geometry will give priority to the animation and not to the simulation. So this is what you saw just now. When the value is set at the maximum positive, 1e plus 10, then this is giving priority to the animation, this geometry. And when we reduce it to the minimum stiffness, that is 1e minus 10, now you can see when we run the simulation now, this whole geometry is not animating, but it is getting simulated. It is getting affected by the pop force that we use in the Vellum solver. So I hope you understand what I'm trying to say. This vellum constraint, in the vellum constraint, the stretch stiffness and the bend stiffness is working as a balancer. So if you increase the stiffness, if you make it maximum, this means that this geometry is going to give priority to the animation, and when you decrease it to the minimum, this is going to give priority to the simulation. And we have to find a balance where the geometry not only rotates or not only animates, but also gets affected by the simulation that we are trying to run here. Like it should get affected by the pop force or any other forces or any other constraints that we are running in the simulation. So this is working like a balancer. Let's create a middle value here. Let's make it 0.01, and let's come to the vellum cloth constraint also, and we have not done anything here. Let's reduce the stiffness here to 10,000, 1 into 10,000. Also the bend stiffness should be reduced to 0.001. Come to the vellum constraints and let's reduce the bend stiffness also to 0.001. Let's run this and see what happens. So now you can see that after we have tried to balance the stretch stiffness and the bend stiffness here in the bend to target constraint, the geometry is not only rotating, not only animating, but is also getting affected by the simulation properties. Come to the vellum constraint and we'll reduce it even more to 0.001, and I think I'll reduce the stretch stiffness in the cloth constraint also to 1000. In fact, let's make it 100 and I'll just multiply it by 5. So this is 500 here. Now let's run the simulation. Let's make a flipbook. Okay, so flipbook is ready and this is our result. So you can see that all these petals are not only following the animation in a way, they are rotating, but they are also getting affected by the simulation properties. So this is what I wanted, but we are also going to include a colliding geometry here, colliding sphere. So this simulation gets more interesting. So let's do that. Let's create a sphere. A polygon sphere. Let's increase the frequency to 10. And this is our sphere. And these are our templated petals here. So what we are going to do is I'll just use a transform node and we will give animation to the sphere according to our petal geometry. For transforming the sphere I am going to use again the sine function. In the x and in the y I'm going to use a cos function. So let's see. So we are getting the animation, but this is not giving a full rotation. So I'll just multiply both of them, the frames, by 3. Let's see if we get a full rotation here. Yeah, so we are getting our rotation, but the radius is too small, so I'll just multiply it by 1.8, and here also multiply it by 1.8. What I want is, I want this sphere to just touch all these petals gently and just move along the way and go away. So I'll multiply it by 2.2. Here also 2.2. Okay, so yeah, this is nice, but I don't want this sphere to start animating from here. So I'll use another transform node, and at frame 1 I'll just move it up a bit to 1.2, 1.4. I'll just animate it, give it a keyframe here, and on frame 20 I want this to come to its original position. So the sphere is starting from here, and then it will come to its original position, and then it will rotate, and at around 90 I will put another keyframe, and at 120 I'll transform it up again to 1.5. I'll create another keyframe here. So this way it starts from here above the petals, it hits the petals, it collides with the petals, and then just move to its original position. Doesn't hit the petals again. Actually, we can increase it to 2. So yeah, this is our sphere geometry, and this is going to be our collider. So let's use a null node. I'll name it collider, and I'll connect it to the vellum cloth in the third input. Now let's run our simulation again, and this is at 147, so I'll press escape. I'll go back to frame number 1. I'll turn off my template here, and let's run the flipbook. So flipbook is done. Let's run it. Okay, and this is what we are getting. The sphere comes, it hits the petals, it collides with them, and in the end also, while it is going out of the frame, it collides with the petal. So yeah, this is looking nice. This is what I wanted. This is great. One more thing that I'll do is I'll just use a vellum post process node. I'll choose the subdivision loop. I'll choose it. I'll increase the subdivision depth to 2. I'll also come to the extrude by thickness. And I'll reduce the thickness scale to 0.025. Actually, just keep the subdivision depth to 1. And instead of loop, make it Catmull Clark. So this is what we are getting, and now I can use a file cache node to cache our simulation. I'll name the cache as Vellum Petals, and this cache, once we hit save to disk, will save cache of the simulation to where your file is saved. So make sure that your file is saved at a good place, because this cache will be saved near to it. Let's just press save to disk. So our file cache is complete. Let's use a null node, name it out, and before we begin the lighting and shading, let's run our final flipbook to see what we are getting. So this is our flipbook. And this is our simulation. This is what we are getting. I'm happy with it. I hope you are happy with your simulation as well. Now what we will do is we'll just begin lighting and shading. But before that, let's create a grid. In the XY direction. And move it behind our simulation with geometry, petal geometry. Let's increase the size of the grid a bit to 1.3. This is okay. I'll copy this grid, bring it here, rotate it. Okay, this is nice. Now once you have find an angle which seems good to you, and the angle that you want to render all your animation in, then just control click the camera so once you find an angle that you want to set the camera at, just control click the camera and the camera will be set there. In the camera, come to view, and I'm going to set it to 1526 by 1920, and I'll also increase the focal length to 85. So this is looking nice for me. I'll just unlock this camera so that it doesn't move when I move in the viewport. I'll bring this geometry, this grid down and come back to camera view. This is nice, and now I'll set some RS slides. Select the slide, move it in the front. This is a bit small, so I'll increase the size of the light. 4.5, or we can increase to 4. Almost 5 here. I'll move it up, and I want this in this direction. I want this light to fall from front top. So this is looking nice. I'll copy this light and I'll bring the second light here behind our simulation. I'll turn it like this. let's move the geometry back a little, and the second light needs to go a little bit back. I'll decrease the size here, 4.2. Let's normalize both the lights, and for the first light, the light at the top, I'm going to bring the spread to 0.7, and for the second light also I'm going to bring the spread to 4.5 something. So this is okay. Come to the camera, and now we will set our materials. Come to the material section, right click and choose RS Material Builder. This is going to be our sim. So this material is going to be applied over geometry. What I want is the colors that we created in our simulation. I want to bring them here. So what I want is the colors that we created in our geometry in our simulation. I want to use those colors as our base color. So I'll use RS point attribute node, this node, and I'll connect. This is already set to CD, which is the color, and I'll set it to base. In the standard material, come to reflection, and we do not want any reflection, so turn the weight to 0 for reflection. And for the subsurface scattering, I'll increase the weight a bit to. For the subsurface scattering, I'll increase the weight a bit to 0.21, and I'll decrease the scale to. Decrease the scale to 1.59. 0.2. Yeah, 0.5. 0.15. And also change the colors a bit. Bring the green down, and also change the colors here. Bring the green down, and this is what we are getting. For the grid, for the background, I'll use Redshift RS Builder again. This is going to be for background, and nothing much needs to be changed here. The only thing that I want to change is I'll choose a blue color, and I'll bring the saturation to 0.9 here. So this is a very light blue color. I'll apply this background to the grid here, and I'll drop down the sim material to the geometry here. And now our materials are applied. As you can see, come to sim, come to render, and we have the material sim. Now we can do our first test render. So now we can do our render, and for that, come to the redshift, click on the redshift button here. This will create a redshift drop and a redshift IPR. Click on the redshift drop. On the output, post effects, just click on color LUT controls for the amplify preview color management. Come to redshift, advance, decrease it to 120. These are the settings that I use for testing purposes, and let's give it a shot now. So let's use a frame in the middle somewhere, like 66. This is looking okay, but what we can do is we can increase the light a bit. So make the intensity for the light on the top 120, and let's run it. So that was our result, and what you can do is to improve it is that come to the Vellum post process, and you can increase the subdivision depth to 2. You can also make your animation more interesting by using a retime node. With the help of retime node, you can add slow motion or fast motion to your simulation. I'll give you an example. So till frame 40, I want the simulation to run at the speed of 1, and at 41, I want the speed to decrease to 0.5. So I'll put one more keyframe here, and I want this to run at 0.5 till 90, and at 91, I'll increase the speed to 2, and then I'll decrease it to 0.5 again at frame 115. I'll just turn this on and make it auto, and let's run flipbook again. Just make sure that when you have changed the size of the resolution in your camera, you have to change the size here as well. So this is our final flipbook with retime node, and you can see that there's a bit of slow motion and then fast motion and then slow motion again in the end. Just make sure that when you're using the retime node that the input frame range is 150. So let's run the flipbook again. So this is our final flipbook. You can see the slow motion and the fast motion, and this way you can make your simulation more interesting. So that was the video, guys. I hope you learned something from it, and I hope that I made the concepts very clear about the Vellum pin-to-point constraints. If not, let me know. I'll make another video, or maybe I'll write an article and share it with you guys. So let me know about it. Please write in the comment section, please share this video, and please subscribe to the channel. For the next video, we'll be creating another cloth simulation in which you will learn about animated pinpoints. So I hope to see you guys there as well. Thank you. Bye.